Okay, hello everyone. Good afternoon. I hope all of you are fine and healthy. Uh, as I mentioned in the announcement, I am going to finish the chapter for analysis of large graphs, link analysis, and page rank in today. And also, I mentioned that in the course outline, we were going to have one more chapter, which was about stream data mining. However, to bring the weight of the final exam down because of the issues that we have, and I don't want to uh, have a big final exam for the students, I decided to move it to optional chapter. So I posted the chapter on Blackboard, but it is up to you if you want. I recommend you to go and learn about stream data mining, but it is not coming on the final exam. So we have no question on the data stream mining. So today we are going to finish the chapter that we talked last time about link analysis. Remember last time we talked about link analysis, and we had some examples of why we want to have this type of application and algorithms. And one of the examples that we used was ranking of different web pages. And we started with the traditional way of ranking the pages and also the traditional search engines. And we saw the issues that we had. And then we mentioned that Google and some other companies provided some good approach and algorithm for new methods of search engine and page rank. We talked about how do we give ranks to different pages based on their importance, and we had the algorithm to first of all to create the stochastic adjacency matrix, and then using the stochastic adjacency matrix and the initial ranks, which was 1 over the number of web pages for every page. Then we had an iterative algorithm to finally find a good adjustment for the ranks for all the pages. Remember, we had this formula that we say, for example, we have the initial rank of R0, and then we had the adjacency, stochastic adjacency matrix, and then we said to create R1, we say, to create R1, we say we create R1 from this multiplication. We multiply the adjacency matrix by the initial rank. And then again, we adjust it by this iteration. And finally, we reach to some adjusted rate, adjusted rank for every page. And then RT is actually a vector that shows the rank for all ranks for all the pages. And we also mentioned about two specific cases. One of them was dead ends. Sometimes we have one or more dead ends inside our graph of the pages. And sometimes we have some type of traps, some type of spider traps. And then we said that we have two strategies to get rid of this issue, dead ends. And we also had one strategy for spider trap. Actually, teleport is working for both dead ends and also a spider trap. But for dead ends, we showed in the example that we can have another strategy by removing the dead ends from out to inside the network, and then create the ranks, and then go back and recreate the dead ends pages. Now we want to continue the chapter by talking some specific thing, especially related to topic specific page rank. Sometimes in the real applications, we have topics and subjects for different web pages. For example, we say these two web pages are talking about health. or these three web pages are mostly talking about sports, or for example, these two pages are talking about politics and so on. So we want to see how we can integrate the topic specific or the subject of pages into the page rank. Means that based on the topic that a user interested to do on the search engine, we are able to give different ranks to the pages. So instead of generic popularity, we want to measure the popularity based on some topic. However, we have some challenges as well. For instance, if the query has a word Trojan, we don't know specifically Trojan is related to the name of a team, which is related to topic of a sport, or Trojan is related to a history fact, therefore the topic is history, or for example is related to the security, and for example one type of security issues, and we have different topics. So we want to have some type of search queries to answer to the interest of the user based on the topic that they select. So the idea is that we have, at the beginning you saw that we have a random walker. When we have a couple of pages, we say that we randomly walk from one page to another page. And then we give some small probability by teleporting different links. Remember, we had teleporting for get rid of dead end and spider trap. We can use teleporting also for considering the topic specific to go to the relevant pages. So the main idea is that how we can use teleporting strategy to make sure that we consider and we integrate topic into the page ranks. So the idea is that we have some type of bias random walk. Means that we consider some teleporting. So the idea is that we pick a set of web pages that are related to that topic that we are interested. For instance, user is interested to sports. Therefore, first of all, we indicate which web page is related to a sport, and then we put them, all of them, inside a set named S. And then we consider some type of teleporting into this specific set. So how we can do that? Remember last time we talked about stochastic adjacency matrix, which was matrix M. And when we say Mij, means that the item inside matrix M, we have pages. Sorry, it is better to make it like this. Remember, we had the stochastic matrix M, right? And then we had different web pages from, for example, 1 to N, and the same thing in here. So therefore, if we have a value in here, means that the link between web page 1 and web page 2, right? From 1 to 3. And then when we say M of ij, means that the element in the ith row and jth column. So this one is the element Mij. And to integrate topic specific, first of all, we create the set S, including all the pages related to that specific topic. And then we adjust the stochastic adjacency matrix M by creating another matrix, matrix A. How we can do that? So we have the set S, including all the web pages that are inside the interested topic. And then we consider a parameter, beta. For example, we say beta is 0.8 or beta is equal to 0.7 with some weight for the beta. And then for every element of the adjacency matrix Mij, if the web page with the index I belongs to the set of interested topic, Then we adjust that element by multiplying that with beta plus 1 minus beta divided by the number of elements that we have inside the topic specific set. And if that row does not belong to the interested topic, then we just multiply it by beta plus 0. And then by having matrix A, this time instead of using matrix M, we use matrix M A to compute the adjusted rank for every page. Let's see some examples. For instance, in here, we have a pair, we have 3 nodes to give me the ranks for to give me the weights for every link. So can somebody tell me what is the rank, what is the weight for every of these links? So what is the rank, what is the weight for this link? Can anyone answer me? What is the weight for this link that I put arrow? We remember that the total weight of every node to other node should be 1. So what is the weight of this node, this link? Anyone? So in here, from node Y, we have 2 links, one going to A and one going to itself. And the total should be 1. Therefore, this one is 1 over 2, and this one is also 1 over 2. And then, if we want to know the weight of the links outcoming from A, so the weight of this one, again, because we have 2 links, the weight is 1 over 2 and also 1 over 2. And then the weight of this link, because we have only 1 link outgoing from node M, the weight of that is 1, right? So if I just want to clean it, it is better to say these are the weight that we have: 1 over 2, 1 over 2, 1 over 2, 1 over 2, and 1. Now we want to consider the topic specific and adjust the ranks, right? So if we want to create adjacent stochastic adjacency matrix, what is the matrix M? So here is Y, A, and M, Y, A, and M. From Y to Y, 1 over 2. From Y to A, 1 over 2. From Y to M, 0. From A to Y, 1 over 2. From A to A, nothing. From A to M, 1 over 2. And from M to Y, 0. M to A, 0. And M to M, 1. So this is the stochastic adjacency matrix for this graph. Now we want to consider the topic specific as S, means that the topics that user interested are Y and A, means that we want to have some bias for these 2 nodes. How we can adjust M and create matrix A, right? We want to know what would be matrix A. Again, Y, A, and M, Y, A, and M. And the parameter beta that we consider is, for example, 0.8, right? So remember, we said that to compute matrix A, for every node Mij, we say if I belongs to the topic, then we say beta times element plus 1 minus beta divided by the number of elements inside S, right? So therefore, we say this is the original M that we had, right? That we had in here. So we say beta times the matrix M plus 1 minus beta, which is 0.2 times this matrix. Why we have 1 over 2? Okay, I think I lost the connection. Okay, now I guess should be fine. So we have this is actually 1 over the number of S, right? So the number of S is, there are 2 elements inside set S, right? Therefore, we have 1 over 2, but for which elements? For those elements that are related to the topic specific, Y and A. Therefore, we have 1 over 2 inside this row and also 1 over 2 inside this row. However, because M does not belong to the topic specific set, this row would be 0, right? Okay, let me clean it a little bit. Therefore, we have to compute these summation. So 0.8 times M plus 0.2 times 1 over S, right? And then if you just compute this, you will see the final matrix M, right? So this is matrix A, that if you compute the top addition, you will reach to that. So instead of this matrix, which is the original matrix M, from now on we use this matrix, right? And then how we can go forward? What was the original vector for ranks? 1 over 3, 1 over 3, and 1 over 3. This is the original, actually we say R0, right? And then we have matrix A. Therefore, we can create R1 equal to A times R0 and R2 equal to A times R1 and so on until we reach to a stable situation, right? So the main idea is that by using the topic specific set and having the original matrix M, you create matrix A that consider the topic specific to adjust the page ranks. Okay, now let's see another example. In here we have 4 nodes and a couple of links between the nodes. First, I want to ask you to give me the weight of different links. What is the weight from 1 to 2? Anyone? What is the weight for the link comes from 1 to 2? Very good, 1 over 2. So we say 0.5. And what about from 1 to 3? Ben? Yes, 0.5 from 1 to 3. And what about link from 2 to 1? 1, correct. and then from 3 to 4, and from 4 to 3. Another? Good. Why 1 over 2? Yes, actually it is 1 because we have only one outgoing from 3 to 4. Therefore, the weight is 1. And also we have only one link from 4 to 3. Therefore, the weight is 1, right? So this is the original weights that we have. Therefore, what is the matrix that we have for M? Stochastic adjacency matrix. We have 1, 2, 3, 4, and 1, 2, 3, 4. From 1, we have 0, 0.5, 0.5, and 0. 2, we have 1, 0, 0, 0. From 3, we have 0, 0, 0, 1. And from 4, we have 0, 0, 1, 0, right? This is the original matrix M that we have. Now we want to create matrix A. Before creating matrix A, first we want to ask what is the set of topic specific, right? So these are the weights. Let me clear what I wrote because I already have it. Okay. So for instance, the topic specific is S equal to 1, means that the only topic that we are interested is this one, right? Now, based on this S, we want to adjust the matrix M to create matrix A, right? The job is to create matrix M, A from matrix M, right? How we can do that? First of all, S is equal to 1, only 1, and beta is 0.8. So we say 0.8 times matrix M plus 0.2 times 1 over S, right? And S has only one element, right? This means that 0.8 times M plus 0.2 times 1, because the number of elements inside S is only one element, right? Now we want to see what are the matrices. So we have 0.8 times, sorry, let me clean that. So we have this matrix M, therefore 0.m times M becomes 0, 0.4, right? Because 0.8 times 0.5 is 0.4. And then 0.4, 0, and then 0.8, 0, 0, 0, 0, 0, 0, 0.8, 0, 0, 0.8, 0, right? This is this one. And then we want to compute this one plus a matrix. The only row that is topic specific is the first row, right? And then we have 0.2 times 1, means that we have 0.2, 0.2, 0.2, and 0.2, right? And then the rest of them becomes 0, right? So this is this matrix, because we have 0.2 and the only topic specific is 1, right? Therefore, we have 0.2 in here, like the one that we had in here, right? In here we had, sorry, I made a mistake, sorry. Let me clear that. Let me clear that. And then we have 0.2 times 1, 1, 1, 1, right? Only for the first row. Only for the first row, right? And then the rest of them would be 0, right? And then if you just multiply this value with these, it becomes 0.2, 0.2, 0.2, and 0.2, right? So we just get rid of this. Now you have the matrix A. Matrix A is equal to addition of these two, 0.2, 1, 0.2, 0.2, then 0.4, 0, 0, 0, 0.4, 0, 0, 0.8, and then 0, 0, 0.8, and 0, right? Before going forward, to make sure that your matrix is correct, you should make sure that the summation of every column is still 1. So every column, the summation of every column should be still 1, right? You can just double check that. If it is 1, then this means that you are correct. Otherwise, it is better to go back and correct your computation, right? So now that you have A with these new weights, let's go back to the graph that we had, right? So in here, the weight from 1 to 1 is 0.2, right? Therefore, we have to have one link from 1 to itself with the rank 0.2. And then you have from 1 to 2 is 0.4, right? And then from 1 to 3 is again 0.4. See, we adjusted the two weights from 1 to 2 and 1 to 3, and we also create a link from 1 to itself by the new weight. Let's go to the second node, link 2. So in here we have 1, right? Nothing will change. From 2 to 1, we still have 1. What about the third column? From 3 to 1, the weight would be 0.2. So we have a new one from 3 to 1, sorry, from 1 to 3. Yes, from 3 to 1, we have 0.2. And then this weight from 3 to 4, instead of 1, becomes 0.8. And what about the fourth link? From 4 to 1, we have 0.2. And from 4 to 3 is 0.8. See here? So we adjusted the weights of all the links, and sometimes we created a new links. That's why we say we do some teleporting, right? So this is the way that we create matrix A from adjacency matrix M, right? By adding some links and by modifying the weights of every node, right? Let me clear that to have, because when I go forward, it actually creates this for you. So this is the new weights of all the links that I have, right? Actually, this one is from 1 to itself, right? So by having a topic-specific page rank, we are able to create a new matrix A from matrix M and using the topic-specific set S, right? So let me clear that. And then we can play with the different values of beta and different set of S. For example, if S is 1 and beta is 0.9 instead of 0.8. Then at the end, the adjusted ranks would be this one. This one is exactly the one that we have in here, right? So at the end, we have the stable ranks, same as the one that we have in here. Or for example, assume that the topic specific pages are 1 and 2, and beta is 0.8. Then we have different values of the rank, right? So to create a topic specific rank, page rank, you need the original links or the original matrix M, and also you need the elements inside the topic specific set S, and also you need the value of parameter beta. And then use the formula that we saw. We can create matrix A from matrix M, and we name it topic specific page rank. Okay, any question at this time? Okay, no more question. Okay, so you need to do practice and do some examples for yourself and create matrix A from matrix M using different elements of S and also different parameter of beta to make sure that you clearly understand how we can create topic specific page rank. Of course, to create the topic specific set S, we can have different type of strategies. For example, remember we had an old website DMOZ. We have different categories. You can figure out different topic specific and then consider topic for every web pages. Or based on the context of the pages, you can consider the topic specific. Or depending on the query and the context of the query, you can consider topic specific page rank for different pages. So you can have different type of policies to consider different topics for different pages. The last thing that we want to talk about in this chapter is about combating with spam. Remember last time we talked about traditional search engine, and we said that we had some way to fool the search engine and give some non-realistic rank to some pages, right? So we want to know how we can combat this issue. So first of all, spamming is all the actions that some people are doing to create some fake ranks for their own web pages, which is actually not related to the real value of those web pages. And spam means those pages that are resulting from the spamming action. So we have very different definitions of spam, but in general, we can say approximately 10 to 15% of the pages on internet are spam. So I just remind you the thing that we had in the early search engine. In the early search engine, the job was to just crawling the page, all the web pages, and then create some indices or ranks based on the words that we have inside different pages. And then we give different ranks and bring them the result to the search engine, right? So the two simple strategies was the number of times that those words that we use inside the query appear in the page, and also the position of those words. Are they inside the header or inside the title? So we can give more weight to them. But we saw that we can easily exploit this type of search engine. So people that are creating spam pages can easily exploit this type of search engine. We saw the example, for instance, a web page for selling shirts. They can put the words sports in their web pages to make it related to a sport, which is actually not. So we saw two different strategies for the spammers. One is to put some words into their pages, and even using the color of the same background color, or we can run the query for that specific topic and then put the content of those related pages into our own page. By having this, we can easily fool the search engine. And all these actions, not only these actions, every action that spammers do are considered term spam. So term spam is the strategy that spammers use to get rid of those type of search engines. Now we want to know how we can get rid of this type of spamming. As you saw, the reason of the power of spammers is that at the early age of search engine, the policy or the base was that what I can tell about myself. However, this is not a good way of trusting to some people. If you want to know about some people, you should see what other people mention about those people, right? This is one way, and also we can consider the page rank that we saw before to have the importance level of different web pages. In this way, we can have some good way of page ranking. However, even with this strategy, some spammers again can fool the search engine by considering spam farming. So after Google provided a new page rank, spammers started to use some new technique again to fool the search engine. How they can do that? They can create a farm of spam, means that a set of many pages that all of them are spam, and then they do some strategy by creating some link spam. What are actually link spam is that they create some specific structure. How they can do that? They can categorize the pages on internet, all the pages on internet, into 3 different types. The first type of pages are those pages that are not accessible. We say those are inaccessible pages. For example, spammers are not able to have access to CNN web page, or they don't have access to, for example, university web page, right? We say these are inaccessible pages. These are good pages that the spammers are not able to access to. The second type of the pages are those that are accessible. They are not spam pages, but they are accessible by the spammer. For instance, you create a blog, and then inside your blog, you give permission to people to write comments in your page. Therefore, spammers can come to your page and put some comments and create some link to their own spam pages, right? Therefore, we say they are accessible page. They are not belonging to the spammers, but the spammers can have access to them. And the third type is actually those pages that are created by the spammers themselves, right? They have the ability to create their own pages, which is some type of spam pages. So if we want to see them visually, we can see something like this. Those pages that are not accessible, spammers can do nothing on them. So they can't change anything in here, and therefore they can't change any link incoming and outgoing. Of course, for their own pages, they can do anything they want. They can create different pages, and they can create different incoming and outgoing links. However, if they have access to some pages that are not actually spam, but they are accessible, means this set, for example, different blogs, then by creating some content like comments inside those pages, they can create some outgoing links from those pages to their own spam page, right? So they can create a spam link to their own page, right? For example, in here, T is a spam page. They not only are able to create incoming and outgoing link from their own pages, they can also create outgoing links from accessible page to those spam pages. Therefore, when we have many links to a spam page, right? All of these are incoming links, right? Therefore, the page rank of this link, this node, will be very high, right? So by creating a spam farm, by having the category of different pages, and they can have some work on the accessible page and their own pages, they can create some fake page rank, some non-realistic page rank for their own spam pages, right? So now we want to know how we can get rid of this type of spam farm. The idea is that we can do two things. First, instead of page rank, we can create trust rank. And also, when we want to consider page rank, we can consider a parameter named spam mass. We want to talk a little bit about each of these two. The first one is trust rank. So when we talk about trust rank, it is a basic principle. Means that we have the principle that good pages do not have an outgoing link to bad pages or spam pages. Therefore, we can distinguish different pages and then give some teleporting or bias to those ranks that are trusted. For instance, I have a site CNN or CBC or BBC or U Windsor or U Toronto or some government pages, right? So we can consider those pages that are trusted and then do some teleporting to those pages because they are trusted pages, right? We say these are trusted pages, and by doing some teleporting, we actually propagate trust to these links, right? So the main idea is teleporting to those trusted pages. However, if we want to figure out which page is trusted and which page is not, we need to inspect all the pages to figure out which one is trusted and which one is not, which is good, which is bad, right? This is one consideration that we have. And also, we want to make sure that every good page get adequate trust. Means that if we have a good page, the trust rank of that page should be high. Means that we can have those good pages reachable when we have random walk here through all the pages, right? So these are two considerations that we have to consider. So suppose we want to pick, for example, K number of pages that we can have some level of trust to them, right? Of course, we can not have a very big value for K, but for instance, we say we want to have 1,000 trusted pages. So K is 1,000. We can have different type of strategies. First, by using the initial page rank, means that you create the page rank, same as the algorithm that we saw, the Google algorithm that we saw. We create page rank for every page. And then from top, we select the K pages with the higher page rank. And then we say these are the trusted ones. Of course, sometimes if we have some spam farms, we might have some spam pages inside the trust rank at the end, right? And the second idea is that we can consider some domains to be trusted. For example, we say every page that has domain education or has the domain government, we can trust them. right? These are the two strategies that we can consider trusted pages to give some higher ranks to them, right? The second idea instead of trust rank is to figure out a spam mass for every single page, right? So far for every single page, we only had page rank, right? For example, inside a network, for example, I say the rank of this page is say 0.2, the rank of this page is 0.8, the rank of this page is 0. For example, 0.05, 0.05, and then 0.1, right? The total rank should be 1, right? This node, and this node, and this node. This is the original page rank that we had, but we want to have a more accurate rank for that. How we can do that? By considering not only the page rank of page for every page, we can also integrate the page rank of page P with only teleporting to the trusted pages. Means that if we consider some pages as the trusted page and we do the teleporting, then, for instance, in here, instead of 0.8, we might have 0.3, for example. Or, for example, this one, instead of 0.2, we might have 0.1, right? Or for this one, we don't have any change. For example, page rank of the regular page rank is 0.1. Also, page rank by teleporting to the trusted page is also 0.1. Now we want to compute a spam mass for every page. So first we compute the regular page rank, then we compute page rank by teleporting to the trusted pages. Now we have these two values. Then we say that the spam mass of page P, the spam mass of page P is the difference of these two, RP and RP plus, divided by RP. So we say this fraction is equal to a spam mass of every page. And then we say the higher the mass of the spam for a page, the higher the probability that that page is a spam, right? For example, for this link, RP was 0.8 and RP plus was 0.3 divided by 0.8, right? So we say, for example, this becomes 0.5 divided by 0.8. So this is the spam mass of this page. Or for example, for this one, the spam mass is 0.2 minus 0.1 divided by 0.2, which is 0.1 divided by 0.2. This is the spam mass for this one. And so on. We can compute a spam mass for every page. And if the value of the spam mass is high, means that with the high probability, that page is a spam. So pages with high spam mass are actually a spam, right? So these are the two ways that we can combat with spamming. The first one, instead of computing page rank, we compute trust rank by teleporting to some trusted pages. And the second thing is that we not only consider page rank of every page, we also consider the page rank of that page by considering trust rank, teleporting to only trusted pages. And then we compute the fraction of a spam mass. And then if the value of a spam mass is high, then we say that page should be a spam. Of course, we can consider some threshold. Say, for example, we say if the spam mass is greater than threshold, then we say this page is most likely a spam. Otherwise, it is a non-spam page. So this is end of the chapter. For the next couple of slides, we only have some summary. We started talking about PageRank, and we said about the Google algorithm for PageRank by computing the stochastic adjacency matrix and initial vector of the ranks, and then finally adjust the ranks. Then we talked about two specific issues. The first one was dead end, and the second one was spider traps. And we showed that by teleporting, we can get rid of these two issues. And then we talked about topic specific page rank, and also we talked about trust rank and spam mask to be able to combat with spamming. Okay, this is end of this chapter, and actually end of all the chapters that we have for this course. And as I mentioned, although we have streaming data mining as the last chapter, but I don't go through that, and I don't ask any question for the final exam from you. So it is up to you to review that by yourself. So next week, we don't have anything to offer to present, because this is the last, next week is the last week. We should not have any meeting. If you have any question, you can just ask me by email, and also during the office hour. And also right now, if you have any question, you can just ask me about. And one more thing, I will send you a practice final exam, similar to the one that we had for the midterm exam. And as I mentioned, I announced on Blackboard, we have a hybrid exam for the final one. I give you a very short online exam, which is some type of multiple choice or fill in the blanks questions, and also a similar exam as a take home. So I will post it on Blackboard, and I give you some time so you can solve and submit your solution at the end of the time period that I give you. The take home exam is similar to the one that we had for the midterm exam, but it is very short. And also the online exam is some type of multiple choice and fill in the blanks questions. Okay, any question that you might have? No question? Okay, if you have anything that you want to ask, you can ask me by email, and if needed, I set an online office hour again. And also I provided a brief survey on Blackboard, and later on it will be available to you. I would really appreciate if you participate in the survey and give me your feedback, so I can use it for this semester, for the final exam, and also for the future offering of this course. And if I see number of questions, some number of general questions for next week, I can put again an online session, so you can join me and ask your questions in a live session. If you have any question, just let me know. Otherwise, I can finish this session. Okay, no question? Okay, thank you very much, and hope you enjoyed the course in this semester, and hope we have a good final exam and final grades for all of you, and not only for this course, for the rest of them. And take care of yourself and your family, and hope you Stay safe and healthy.